All right, so we're going to look at section 8.3, parametric equations. So as you can read right here, up to this point, we've been presenting a graph by a single equation involving two variables, x and y. In this section, you're going to study situations in which it's useful to introduce a third variable to represent a curve in a plane. When vectors are used to solve problems of motion, the components of the vector is various functions of time. For example, this vector xy might have x representing some function of time and y representing a function of time. Okay, time is called a parameter. So that's what we're looking at. We're going to look at parametric curves and parametric equations. So what are these things? The graph of the ordered pairs xy, where x is these other equations based off of t, are functions defined on an interval of t values. This is a parametric curve. The equations, those, are called parametric equations for the curve. The variable t is called a parameter, and I is called a parameter interval, the interval for which t is defined for. Sometimes that can be the entire number line, all the real numbers, and sometimes it might be just a small set of them. So we're going to look at how to graph these things. How do I graph a parametric curve? Okay. We still plot points in the xy plane. Each point, though, is determined by values of t. So what you're going to be doing is this. We don't make an xy table, we make a t xy table. We plug in values of t into the given from the given interval into those parametric equations to find an x and a y. And then you plot x and y. One of the main reasons for parametric equations and stuff like this is that I can take a graph or an equation that is not a function and represent it as parametric equations, which are functions in relation to time. And that allows me then to do certain aspects of different things. So we're going to sketch a graph right here. We're going to sketch this curve where x is defined as t squared minus 4, y is defined as t divided by 2, and t goes from -2 to 3. So we're going to graph that. Let's go ahead. I got it set up over here. Okay. So just like we said right here, we're going to plug in values for t into these equations to get an x and a y associated with it. So just adds another little layer. So t goes from -2 to 3. So we're going to plug in all those integers between, like so. You take -2, you plug it in here. -2 squared is 4. 4 minus 4 is 0. So when t is -2, x is 0. Take -2 and plug it into here. I get -2 divided by 2, which is -1, which means y is -1. And we just continue this process all the way down until we have all of our values. So speeding this process up, plug in -1, I'm going to get a -3. Plug in 0 gives me -4, -3, 0, and then a 5. If I plug in the other numbers, the t into over here, I'm going to get a -1/2. Then I'm going to get 0. Then I'm going to get a 1/2. Then I'm going to get 1. And then I'm going to get a 3/2. So the t helped us find x's and y's, and now we're going to graph just the x's and y's. So we're going to put a dot for all of these things. So 0, -1, 0, -1. -3, -1/2. -4 is 0. -3, +1/2. 0, 1. And then 5 goes to 1/2. This was the start value. This was the end value. So this is the start value here. This is the point 0, -1. This was the end, 5, 3/2. And you can see that it's basically a parabola, or part of a parabola on its side. There's no arrows on the ends because t stops at 3 and -2. If it kept on going all real numbers, then there would be arrows on the ends. Here's a key point here. You can label this one up here. And that is a parametric curve. Okay, and that's how you would graph these things. Again, this right here says, notice that there's no arrows on the ends because t was on a defined closed interval. If there's no interval given, then assume t is defined for all the real numbers and the arrows are needed. Okay? So you can see there's the graph that we just did. The next thing we have to be able to do is sometimes I want to go back to the x and y equation with no t variable in it. So we want to eliminate the parameter. So how do I do that? Well, you solve, basically it's just a system. You solve one of the parametric equations for t, substitute into the second equation using parentheses, and then simplify until you get an equation that just has x and y in it. If you can solve for x or you can solve for y, do so. If you cannot, that's okay. Because these are not always going to be functions. You may not always be able to solve for x and y. But if you can go ahead and do so. If you can't, you can just leave it in whatever format that you have. So here's an example we're going to look at. A couple of them I have right here. Let's go ahead and solve these. Here's the one we just did. So what does this equation look like? Okay. I didn't put the interval on here, so I'm not going to worry about that. So I need to solve one of these for t. Obviously, this is the easiest one to solve for t. So multiply both sides by 2, I get t is equal to 2y. So if t is 2y, then I can plug it into this thing. And then work that out. And so then x equals 4y squared minus 4. And it's solved for x, and we're good to go. And there's your xy equation. We already know this is not a function, so it's not a y equals, it's going to be an x. But I have trig stuff involved. If you have trig stuff involved, you need to keep in mind some of the identities that are associated with the trig stuff. Most likely, there's a bunch of them, but most of the time they're going to use kind of like the Pythagorean identity asking. So in other words, you're going to look at the identity, the sine squared plus the cosine squared equals 1. And when I do that, I can take this equation and solve for cosine. I can solve this one for sine. And then I can take these and substitute it into that. So if sine squared plus cosine squared is 1, then x over 3 squared, y over 4 squared must equal 1. And that's how I can use the identities to help me write equations with sines and cosine stuff. Working this out, you get x squared over 9, y squared over 16 is 1, and you are done. Okay? We're going to revisit the projectile motion problem. Projectile motion is launched from a point y sub 0 feet above the ground with an initial velocity of v sub 0 feet per second at an angle of theta with the horizontal. Because this is describing kind of a vector, I can look at this as the initial velocity can be modeled by this vector right here. Okay. See how we're breaking it up into its component parts. The path of a projectile is modeled by parametric equations. This equation right here describes the horizontal change in position and this describes the vertical change in position. Okay, so that's how a lot of your physics problems and such come into play, and how that we've only been using this one and only discussing the height of a projectile, but I can now break it apart and look at it as two parts. This is the horizontal distance, this is the vertical distance. And so with that, we can answer questions like this. So Kevin's going to hit a baseball at 3 feet above the ground with an initial speed of 115 feet per second at an angle of 18 degrees with the horizontal. How many seconds after he hits the ball will it reach the wall? So in other words, he's going to hit this thing, and he's going to aim it toward the wall. I left that part out. So the wall is, I forgot to tell you how far the wall was. I think the wall is like 400 feet away. 400 feet away. How many seconds after he hits the ball will it reach the wall? Or does it reach the wall, actually? How high is the ball when it reaches the wall? And does the ball clear the 20-foot high wall? Okay, so the first one is talking about after how many seconds will a ball hit the wall. So that's a horizontal thing. And so I can use this information and the parametric equation that we talked about. So x equals the initial velocity, the cosine of the angle times t, and I can plug into that. So the distance it's going to travel is going to be the 150 times the cosine of 18 degrees times t. The distance to the wall is 400 feet. So then to find t, I need to divide this out. And you can use your calculator to approximate this, and you'll get an answer that's about 2.804. T is in seconds, so that is in seconds. So we will reach the wall or hit the wall in 2.8 seconds after being hit. The next question is how high is the ball when it hits the wall? And then this is a secondary question of the same thing. Will it clear? Basically, it's going to be over 20 feet. When I reach that wall, is that ball going to be over 20 feet tall? If it is, then it will clear the wall. If it doesn't, then it will hit the wall. And so that uses the other equation that we had. This is the vertical aspect of things. And the initial height. So we plug in the numbers that we know from this one. We want to know the height of the ball. Excuse me. It reaches the wall at 2.84 seconds. So let's plug that in. 2.804 squared. Initial velocity is 150. The sine of the angle is 18 degrees. And we're going to times it by 2.804. And the initial height is 3. So we plug all the information into that, and then we can use our calculator to approximate this out. And when you type all that in, you're going to get 7.174, and that'll be in feet. And what does that mean? That means when the ball reaches the wall, it's going to hit the wall at 7.174 feet. And so then the answer to the last question is, does it clear the wall? And the answer is no. Okay? The ball hits the wall at 7.174 feet from the ground. It will not clear the wall. And that's how you can use it. Parametric equations for vertical motion to solve some of your problems. Okay, so that ends this video. We'll take more questions in class.